Right, so that is how we can show that f of 0 de e is going to give us un 0 de f. So the procedure is very simple, or the process is very simple. All you have to do is to just understand what is happening here. So we've chosen some lambda. We fixed it at, we've chosen some lambda is equal to 0, and then we've taken some element x in E. Okay, and then the element lambda multiplied by x is going to be in E. Why? It is because E is an espace vectoriel. It is stable by addition. It is also stable by scalar multiplication. So the element lambda multiplied by x here is a scalar multiplication I'm performing here. So lambda multiplied by x is going to be in the space E. Or lambda is equal to 0. So 0 multiplied by any element x in E will give me 0. But what 0 are we talking about, to be specific? Or because lambda multiplied by x is an element of E, so the 0 I'm talking about c'est un 0 de E. Même chose, f is a mapping that associates every element x in the set in the espace E, or every vector x in the espace E, to a vector f of x in the espace F. So if I take f of x is if I compose x by f, if I say f of x, then f of x is going to be an element of f. Or f is an espace vectoriel, so it is stable by scalar addition, and scalar multiplication. So the item lambda multiplied by f of x is an element of f. Now because lambda is equal to 0, 0 multiplied by f of x says 0. But what 0 are we talking about, to be specific here? Oh, lambda multiplied by f of x is an element of f, and so the 0 we're talking about here c'est un 0 de f. Bien, so let's look at f of lambda multiplied by x. Now we know that f est une application linéaire, so this property is true. So f of lambda multiplied by x is lambda multiplied by f of x, because car f est une application linéaire. Or lambda multiplied by x, because lambda is 0, c'est un 0 de e, so we replace 0 de e here. And then lambda multiplied by f of x, c'est un 0 de f. So that's why here we have f of 0 de e is equal to 0 de f. And then that's the first property. Now the second property that we have here is, the demonstration is by mathematical induction or par récurrence. So the idea here is that this property that we have here for the sum, so we sort of like combine these two properties. The first property f of u plus v, and the second property f of lambda u, and the second property, which is f of lambda u is equal to lambda multiplied by f of u. We combine these two properties, but then not only for two vectors, but for n vectors. So this is like some generalization. So it's very simple to sort of like prove this, but then the proof is by mathematical induction. But then because it's very simple and you can sort of like understand by just, looking at the definition of une application linéaire and sort of like wrapping your head around, the fact that around the idea that we've, combined these two properties that we have here. So this is like some generalization. Instead of only considering two vectors, it's also true for n vectors. Okay, so this is what the second property is saying. Now let's look at some examples to see how we can apply, the definition to show whether a given application is une application linéaire or not. So let's look at the first exercise. Dire si les applications suivantes sont des applications linéaires. So premier exercice. So we have the first one here is, we have a function f from r squared to r3. Okay, so and then that associates to every couple x comma y the vector x plus y comma x minus 2y comma 0. Is this a linear application? Now let's first of all inspect. Let's first of all look at what is happening here. So remember, this is our E. This is our espace vectoriel E, the first espace vectoriel. The second one is our espace F. So is this a linear application? So for this to be a linear application, according to the definition, we must check for two things. The first thing that we must try to verify is that if I take any two elements, soit x, y, if I take any two elements in E, donc soit X et Y, two elements in E, in this case E is equal to R squared, the first thing that I want to check here is that is f of x plus y equal to f of x plus f of y, like so. And then the second condition I must check here is, and let's also take a lambda, so lambda a scalar in R. Here we take lambda a scalar in R, like so. Because k, we know that k is either R or C, just like I said. So we also need to show that f of lambda x is equal to what? Is equal to lambda and then f of x. So let's look at the first condition. Let's look at the first condition we have here. Let's look at the first condition we have here. So let's look at the first condition we have here. So for the first condition, so let's first of all, so we've taken some two vectors, x and y. Now each of these two vectors, each of these vectors have two what? Components. Each of these vectors have two components. R2 here, look, here our E is R2. So maybe what we can do here to simplify things is, let this x be U. Let this x be U, like so. You see why I've chosen U and V, for example, U and V. So because it's easier to see, to see vectors, as having components along the x-axis and along the y-axis than maybe any other naming that is available. So this is f of U plus V, like so, and then here we have f of U, and then here we have f of V, like so, and then here we have lambda U, and then lambda V here. So this is what we're supposed to show. Now U and V are elements of R2. Now all elements in R2, or all vectors in R2 have two components. So U has some x component, it also has some y component. V also has an x component. Now to place a distinction between the x component of U and the x component of V, I'm going to call the x component of V x prime, and then the y component y prime, for the same reason. So U and V are elements of what? Are elements of R2. All vectors in R2 have components, an x component and a component along the x-axis and the component along the y-axis. Simply put, so U has two components and V has two components. Now let's look at U plus V. Now U plus V is, how do we add two vectors? Well, we add two vectors by adding the corresponding components. So here U plus V is, we add the x components, so it will give us x prime. Then we add the y components, it will give us y prime. C'est très facile, like so. Now I can also write it like this. So x plus x prime, and then y. So x plus x prime, and then y plus y prime. So this is the vector U plus V. So let's now apply the function f to this sum. So to this sum, f of U plus V. So according to the way the application is defined, if we apply this application to some vector U, if we apply this application f to some vector U, well, we get this item. We get this item that is here. So we get the item, we get a vector where the first component is x plus y, and then the second component is x minus 2y, and then the third component is fixed at 0. So if I apply f to this new vector U plus V, because U plus V has given us a new vector. U plus V has given us a new vector. So this is like the first component, and then this is like the second component. So if you look at this application, the way this application is defined, the x that we have here, we take it as x plus x prime. And then the y that we have here, we take it as y plus y prime. Because U plus V is another vector in R2, okay? It's another vector in R2. Then the components are x plus x prime, y plus y prime. So if we take here, if we substitute for x plus x prime, and then we substitute for y plus y prime, and then inject these into whatever we have on the right, then would have found our result. So this is going to be equal to, so we do what I've just what I've just said. So this is going to be x plus x prime for x, and then plus y prime for y. I'm just substituting here. The y is y plus y prime. The x is x plus x prime, like so. And then comma. And then we have x plus x prime, like so, minus 2y plus y prime, like so. And then comma, the third component is fixed at 0. Bien. So another way of writing what I've written here is writing this vector. So I can write it as x plus y. Now you see why I've written it like this in a moment. So x minus 2y, and then 0, and then plus x prime plus y prime, and then x prime minus 2y prime, and then the third component is fixed at 0. So what I've done here is I've separated the components of x. I've put the components of u. I've put them on one side, and then the components of v, I've put them on the other side. And then if I perform the sum between the corresponding components, or the corresponding components of u and v, I'll get back the result that I have here. I'll get back this result that I have here. Oh, what is this item that we have here? Well, this item is f of u, and then this item is f of v. Because why have I said that the first item is f of u? The form, if you look at the form of this particular, vector, you can see that it agrees with this definition here. X plus y, x minus 2y, comma 0. Same thing. The second one also agrees with this form that has been presented here. So x plus x prime, and then comma x prime minus 2y prime, comma 0. So here we've shown that actually this first property is true, quel que soit u and v, because our choice of u and v in E is arbitrary. So f of u plus v is equal to f of u plus f of v. So the first property has been verified. Now let's look at the second property. So de même. So de même. So we can also see what f of lambda multiplied by u is. Now let me remind you that lambda is coming from r, and then u has two components, one component along the x-axis and then one component along the y-axis. Simply put, now u is an element of R2. We know that lambda multiplied by u is, we multiply every item or every component of u by lambda. So this is scalar multiplication. So lambda multiplied by x, and then lambda multiplied by y, like so. So what is f of lambda multiplied by u? So to find what f of lambda multiplied by u is, we have to look at again the form. So here our x, will substitute the x that we have here. The x that we have here, will substitute it with what? The x that we have here, will substitute it with Right, so I had a connection problem. Yeah. So what was I saying? So what was the last thing I said? What was the last thing you heard me say? What was the last thing I said, Natasha?
You are saying that you are doing the first talk. Saying that you're doing the last part.
I was showing the second property. I was checking the first second property.
Yes, for the
Okay. Right, so
second, yes.
yeah. So for the second property, we're supposed to show that f of lambda multiplied by u is equal to lambda multiplied by f of u. Okay? So we know that u is an element of R2 or is a vector in R2, meaning it has two components, an x component and a y component. Oh, lambda multiplied by u is scalar multiplication. So I'm scaling the vector u by lambda, by the quantity lambda. Meaning, I'm going to multiply lambda by each and every component of what? Of u. And so, lambda multiplied by u is lambda x, comma, lambda y. Okay? So it means that the lambda x here, the x that is here, we substitute it with lambda x. And then the y that is there, we substitute it with lambda y. And so, if we do that, what are we going to get? We're going to get, if we apply the function f, well, the result is on the right. Okay, the result is on the right. So we're going to have lambda x plus lambda y, and then comma, lambda x plus lambda y, comma, lambda x minus 2 lambda y, and then comma 0. Now here you can see that we can factor out a lambda, because here we can say we can factorize by lambda and then x plus y, like so, and then comma, and then we can also factor by lambda here. We can also factorize by lambda. We can have x minus 2y, like so, and then comma 0. Oh, we can take out the lambda now. So lambda, and then x plus y, and then comma x minus 2y, and then comma 0. Now this is going to be equal to, and then lambda. Oh, this is my f of u. This is my f of u. This is the way f of u is defined. So this is my f of u. So we've seen that the two conditions have been what? The two conditions have been satisfied. The two conditions have been satisfied. So the conclusion here is very simple. Donc, f est une application linéaire. Est une application linéaire. Like so. So f is a linear application because we've satisfied the two conditions. Now let's go back to one important detail here. We said that the first property, where is the property? Let me just, this first property here, f of 0 de e is equal to 0 de f. This is a necessary condition. Okay? So because we've shown that f is a linear application, then we already know, we must know that this condition has already been checked. Because f is a linear application. So we've applied the definition, we've shown that f is a linear application. Okay? So automatically, that first property is true. Now, if you're curious or you are skeptical, you can sort of like try to see, you can try to check, you can try to verify that actually the first condition is true. Now, I'll tell you that directly that yes, it's true, but you can check. For example, what is the zero element of R2? Let's look at the zero element of R2. We know that the zero element of R2 is what? Is 0, 0. Like, so it's a zero vector that has two components. 0 along the x, 0 along the y. Okay? So, f is a linear application. F is a linear application. So, we want to check if this property has been verified. We want to check if f de 0 de R2 is going to give us an 0 de R3. So, let's get this vector 0, 0 and apply the function f. So if you apply the function to 0 de R2, what are you going to get? So x is 0, so you have 0 plus 0, And then here you have 0 minus 2 multiplied by 0. And then you have 0 like so. Oh, this is 0. And then this is 0. And then this is 0. And then this is equal to 0 de R3. So you can see that this condition has been checked by virtue of, f being une application linéaire. So if f is une application linéaire, this condition has already been checked. So this is a necessary condition. This is a necessary condition. Now, let's look at the second problem here. The second problem. Now, for the second problem, you don't have to waste your time. You don't have to waste your time trying to check these... Is the screen appearing? Is the screen appearing? Normalement, non. Are you able to see the screen? Right, so I had another connection problem. So, are you able to see the screen?
Yes, you can see.
Très bien. Bien. So, I was saying, for the second one, we don't have to waste our time. We don't have to waste our time because it's looking suspicious. Let's first of all examine. Let's examine the first one. Okay? I mean the second one. Let's examine the second one. You see that it's actually looking very suspicious. And it actually is telling us that we don't have to waste our time, trying to sort of like verify the two conditions. Now, let's look at what I said about this property that we have here. So this is an extremely powerful property. And we can always try to sort of like wrap our minds around, this property. Okay, and sort of like remember it each time we are solving questions, that have to deal with, us demonstrating or showing that some certain application or some certain mapping from an espace vectoriel to another espace vectoriel is a linear mapping. So we can sort of like try to use that property. Let's examine the second one. The second one here has a 1 instead of having a 0. So this should tell you something. If you look at the first one and the second one, the difference is that here the last item, the last component here is 0. And then the last component here is 1. Everything else is the same. Okay? So they've just changed. They've replaced the 0 with this one that we have here. Now, if f is a linear application, then f must map the identity element of R2 to the identity element of R3. If f is indeed a linear application. So this is a necessary condition. It is a necessary condition. So let's check if this condition has been checked. Let's check if this condition has been verified. So what is the zero element of R2? It is the zero vector that has two components, 0 along the x, and then x-axis, and y along the and 0 along the y-axis. Simply put, so this is what we have. That is 0 of R2. Now let's plug in the 0 here. 0 for x, 0 for y. You see that we're going to get the vector. This is going to give us the vector 0, 0, 1. Now this is not equal to the 0 vector of R3. So the 0 vector of R2 is mapped to something else. It is not mapped to the 0 element of what? It is not mapped to the 0 element of R3. Okay, it is mapped to something else. And so f is not a linear application. F is not a linear application. Is it clear? For the second one, don't waste time trying to check the two properties. Don't waste time trying to check the two properties. Say 4. F is not a linear application. So you can just sort of like catch it directly here by just sort of like trying to see if the 0 element, so it's a necessary condition. It's a necessary condition, yes. So it has to work. So here we've seen that it works for the second item, for the first problem, but for the second problem it doesn't work because of this one. So the 0 element of R2 is mapped to something else, which is 0, 0, 1, that is not equal to the 0 element of R3, and so this cannot be une application linéaire. Okay? Is it clear for the first two problems?
Yes, very good.
Très bien. Now the third one is also looking very suspicious. The third one is also looking very suspicious. Why is it looking very suspicious? Now, anything that is linear, linear equation, linear expression, linear whatever, if you look at all the variables in that particular expression or equation, they should have the highest degree. The highest power should be 1. The highest power should be 1 if anything is linear. For example, the equation x plus y is linear. The equation x squared plus 2x plus 1 is quadratic. It's not linear because the highest power there is 2. Then you can also have something that is known as a polynomial, where you have powers like x, where you have x terms like x to the power 3, x to the power 4, and all those terms that we have there. So the third one, if you look at the third one, it doesn't look like a linear application because I'm seeing quadratic terms like x squared and y squared. So this one cannot be a linear application. Now, this is, by just looking at this is what I'm saying. Okay, this is what I'm justifying. Okay, this is my justification to you. If you plug in the 0 element, the 0 element, if you try to see if actually this application f maps the 0 element of R2 to the 0 element of R, you see that it works. Because the 0 element of R2 is 0, 0. So this condition is not sufficient. Okay. If you plug in your 0, 0 in for x and for y, you get 0 because x squared is 0 squared minus y squared is going to be 0 squared. So you get 0, which is the identity element of R. However, the condition is not sufficient. It's necessary but not sufficient. Okay. So how do we sort of like, without checking the two properties, how can we show that actually the third one is not a linear application because it has quadratic terms or terms like x squared minus x squared and y squared? Well, we have to look for a counter example. We have to look for a counter what? We have to look for a counter example, and then we'll look for a counter example that is going to disqualify either the first condition, which is f of u plus v is equal to f of u plus f of v, or the second condition, which is f of lambda u is equal to lambda f of v. So in other words, we want to look for a counter example such that f of u plus v is not equal to f of u plus f of v, or f of lambda u is not equal to lambda f of v. So that is the counter example we must look for. So this cannot be a linear application. And so how do we show that without sort of like using words? So we have to look for a vector or a counter example such that either the first property is going to be false, or the second property is going to be false. So let's look at one very funny example here. So let's look at the vector 0, 0. So prenons, for the third problem, prenons. Let's take the vector u is equal to this vector that we have here. So let u be equal to the 0 vector. So 0, 0. So, and then we know that this vector 0, 0 is equal to what? The vector 0, 0, I can write it as f, or I can write it as 1 plus 0. I can write it as 1 plus 0 and then plus minus 1 comma 0. It gives me the same thing, because if you add the corresponding components here, y plus minus 1 is going to be 0, and then 0 plus 0 is going to be 0. So you get that particular vector. Now let's try to check the first condition. So I'll keep this vector like so, and then I'll also keep these vectors in mind like so. Right, now let's look at f of 0, 0. Let's look at f of 0, 0. Now let me write it in this way to sort of like make things a bit clear here. So I'll say f of 0, 0 like so is equal to what? F of 0, 0 is equal to 0, right? We know that it's equal to 0. Why? Let's check. If you check here, if you plug in your 0, you have 0 squared for x. If you plug in your 0 for y, you have 0 squared for y, and so you get 0. This is clear. This is clear. But then let's look at f of 1, 0. What is f of 1, 0? Well, f of 1, 0 is 1. F of 1, 0 is 1. What is f of minus 1, 0? It's also equal to what? It's also equal to 1. Okay? It's also equal to 1. Okay? F of 1 minus 0 f of minus 1, 0 is also equal to 1, because minus 1 squared is what? Minus 1 squared is 1. So it gives us the same thing. Oh, what do we see? If you combine, if you sort of like look at this, we have that f of 0, 0 is not equal to f of what? Is not equal to f of 1, 0. Is not equal to f of 1, 0 plus f of what? F of minus 1, 0. This is a counter example. So the first property has been defiled. So the first property is not true. So this cannot be a linear mapping, because if it has to be a linear mapping, the first two conditions are supposed to be true: stability by addition and then stability by scalar multiplication. Okay, but then here we see that for the vector 0, 0, which is our counter example, this is not equal to f of 1, 0 plus f of minus 1, 0. This is a natural decomposition, one possible decomposition of the vector 0, 0. You can also decompose 0, 0 into 2, 0 and minus 2, 0, or 3, 0 minus 3, 0. C'est exactement la même chose. All you just need is one counter example to disqualify one of the two properties we're supposed to check if a particular application is to be linear. Okay, so these are the three exercises sort of like help you understand the definition and how you can apply the definition and the necessary condition, which is not sufficient to sort of like solve problems like these problems that we have here. Okay, bien, je passe. Hopefully the connection is okay, still there, so we're still connected. Je passe. Très bien.
Yeah, okay. Can you just repeat one more time on the example?
Okay. The third example has quadratic terms. It has terms like x squared and y squared. So by just looking at this particular problem, it cannot be a linear. It cannot be a linear mapping. It cannot be a linear mapping. So in this case, we have many proof techniques we can use. We have many proof techniques we can apply here. But then the one that we apply in cases like the one we have for exercise 3 is we look for a counter example. We just look for one example of one vector that is going to disqualify. Just look for one vector that is going to disqualify one of the properties here that we are supposed to show. Either we look for a counter example that is going to disqualify f of u plus v is equal to f of u plus f of v, or a vector or an example that is going to disqualify f of lambda u is equal to lambda multiplied by f of v. So we look for such a vector. We look for such a vector that is going to disqualify one of these properties, because just by looking at this has quadratic terms. It cannot be a linear mapping. But how do I prove that? In situations like this, we look for a counter example. So I chose the zero vector, 0, 0 as a counter example. Now 0, 0, we know that it can be written as what? 0, 0 can be written as 0, 0 can be written as 1, 0 plus minus 1, what? 0. Okay, or you can write it as 2, 0 or minus 2, 0, or 3, 0 minus 3, 0. You can choose, whatever decomposition you want here, but then that is not going to change the fact that 0, 0 can be decomposed in some sort of way as a sum of two other vectors. Okay, now let's look at f of 0, 0. F of 0, 0, if you plug in f of 0, 0 into this particular mapping, you get 0, because x is 0 and y is 0, and so 0 squared is 0, and then minus y squared, which is minus 0, is going to be equal to what? Is going to be equal to 0. If you look at f of 1, 0, you get 1, because you have 1 squared minus 0. If you look at f of minus 1, 0, you get minus 1 squared minus 0, which is 1, like so. Or f of 0, 0 is not equal to f of 1, 0 plus f of minus 1, 0. So looking at this 0, 0 that I have here is the sum of two vectors. This 0, 0 is the sum of these two vectors, 1, 0. Now this is your u. If you want to compare with the first property, this is like your u, and then this is your v. And then what I have on the left here is u plus v. What I have on the left is u plus v, and then this is my u, and then this is my v. Now this is u plus v, and then this is u, and then this is v. So I have f of u and then f of v. So we see that f of u plus v is not equal to f of u plus f of b, because f of 0, 0 is not equal to f of 1, 0 plus f of minus 1, 0. So the first property is not true, and so because the first property has been disqualified, we cannot say that the third application is a linear mapping. So we violated the first property. So you just have to look for a counter example that violates either the first condition or the second condition. If any of the conditions is violated, then the application cannot be a linear mapping. So how was I able to know that I'm supposed to pick a counter example? Is because of these quadratic terms I'm seeing here. So this cannot be a linear mapping, because I have terms like x squared and y squared, which are going to be in a quadratic expression. Here we are saying linear, so the highest degree in the highest power has to be 1. Okay, all the terms must have a power that is at most 1. At most 1. That is the second example. Is it clear? Or the third example, sorry.
Yeah, it's clear. Now let's suppose it was x minus y. So in that case, it will be.
If it's x minus y, yes, it will be a linear application. I mean, you have to check the two conditions. You first of all check the two conditions before concluding. You check that f of u plus, that if you choose any vectors u and v in E, that f of u plus v is going to be equal to f of u plus f of v, and that f of lambda u is going to be equal to lambda multiplied by f of lambda u. So this is what you're supposed to. You check the two conditions. In that case, you already have a linear expression. So to be sure that it's a linear mapping, you check the two conditions that you're supposed to check. So the procedure is going to be different. So we follow the normal procedure. Bien. Now here is a very, very, very concise, expression of the. This is like sort of like getting the two properties and combining them into one property. So normally, to show that some application is a linear application, or to verify or check if some application is a linear application, normalement we have two conditions. we are supposed to check. Oh, network problem. Let me. Right, again. Okay. So normally we're supposed to see if f of u plus v is equal to f of u plus f of v. And then secondly, we must just see if f of lambda u is equal to lambda multiplied by f of u. Now, this is a very, very sort of like nifty and concise, property that sort of like groups the two conditions into one condition. So instead of like applying the two conditions, you can sort of like apply this condition, and then if this is true, then you arrive at proving whatever it is that you are proving. So to show that f is a linear application, instead of checking the two conditions, you can just apply, or you can just check to see, or you can just see if this property. You just check for this property instead of checking for the two separate properties. You just check for this particular property. So you take any two elements in E, and then you take any two scalars in K, and then you have to check if f of lambda multiplied by x plus b multiplied by y is equal to alpha multiplied by f of x plus beta multiplied by f of y. So if you check if that is true, then it's going to be a linear application. So instead of like showing these two properties separately, you can sort of like check for this one condition, and then you would be doing the same thing. So that is what we are saying here. And then it's the same thing that I've already talked about this. Like, you're supposed to just check this one property instead of like checking the two conditions separately. You can just apply this one property, and then you would be doing the same. You'd be doing the same thing. So now, how do you show? Pour montrer que f n'est pas linéaire, you check for the first condition. You check that this. Remember, you check for the necessary condition. What we did for the second exercise, for the second example, we just verify. We just used this condition. Does the application map the zero element of E to the zero element of F? If no, then it cannot be a linear application, because this is a necessary condition. Every linear application must satisfy this condition. If it is not satisfied, then the application is not a linear application. So either you check this condition, or you check that this property, this very long property, this one property, it has been violated. Any of these conditions is going to either of these conditions is going to sort of like work. Okay, you check for the violation of the first property, or you check for the violation of this one property that we have here. So it's going to work. Yeah. So we've already used the first one for the second exercise. You can also try to apply this long this one property that we have here. You can also check for this property for the second exercise. Vous aurez la même réponse. So that is what we have here. Then I'll quickly pass like so. What do we have here? We have this. Okay, let's look at let's look at this corollaire, or we look at this proposition. Soit E et F, deux cas espaces vectoriels, et F une application linéaire de E dans F. On suppose que E est de dimension finie. Remember, let me remind you that the dimension of an espace vectoriel is the number of elements in the base of that espace, and then all the basis vectors of that particular espace are going to have the same number of elements, and that number of elements is what we are calling the dimension of that particular espace vectoriel. Bien sûr, fini in this particular case. Et on distingue, so we have a base. Remember, we also have what is known as la base canonique. I'm just reminding you what la base canonique. It's like the most natural basis system. Okay, the basis system that we can have. The base canonique for l'espace R2, it is 10, 01. And then for R3, we have 100, 010, and then 001. So c'est la base canonique, la base la plus naturelle. So that is what la base canonique is. And then pour tout vecteur x de E, we have that f of x is equal to x1, f of e1 plus x2 f of e2, and then plus dot 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 plus xp f of ep. Where Now this is very easy to see. This is very easy to see because look, E is an espace vectoriel, and then I'm saying that E has a basis B. E has a basis B. E is an espace vectoriel. It has a basis E. Now automatically any element, so quel que soit x, any element x that I take in E can be decomposed in the following way. X E1 plus x2 I2 plus x3 I3, and then plus dot 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 dot, and then plus xn En. Why is this so? Remember, la base d'un espace vectoriel, c'est une famille génératrice. C'est une famille qui est à la fois génératrice et libre. Okay? It is a family of vectors that is generatrice, meaning it is capable of generating the entire space E. It is also libre. So the property that you are seeing here is, the aspect of generatrice, because every element x in E can be written as a combinaison linéaire of the elements in this particular base. So we looked at these things. Okay, we looked at these things. Any vector x can be decomposed, in this particular way, where x1 and x1, x2, and x3 up to xn are known as the coordinates. Are known as the coordinates of the vector x in this particular basis system that we have here. So you get this proposition, or you get this corollary if you apply f. If you apply f, what are you going to get? So f, you have f of x is equal to, f of x1 E1 plus x2 E2 plus dot 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 dot, and then plus xn En. Or f est une application linéaire. And then there's this second property that I showed you, the one that we're supposed to demonstrate par récurrence or by mathematical induction. This one, let me just quickly go back to that particular property. Here, this second property here, we're supposed to demonstrate it by par récurrence. I described how we can sort of like try to show that this is actually true. So this is what we will apply. F est une application linéaire, and so because f est une application linéaire, what is going to happen? What is going to happen here is that, so we are going to have f of x1 E1 plus f of x2 E2, like so, and then plus dot dot dot, and then plus f of xn En, like so. Again, f est une application linéaire, so we know that f of lambda multiplied by some vector is lambda f of that particular vector. So here we have x1 f of E1 plus x2 f of E2, and then plus dot dot dot, and then plus f of xn, and then En. So you get this. So this is how you can sort of like think about how you can get this second property. And of course, I'm using n here as the index of the last element in the basis B. But then here they're using P, mais c'est exactement la même chose. C'est exactement la même chose. So this is how they arrived at this particular result here. By just remembering that x, because E is an espace vectoriel, and if I take one of this, one of its bases, then x can be decomposed into elements, or x can be written as a linear combination of the elements of that particular basis, because une base, c'est une famille qui est à la fois génératrice et libre. Okay, so this is the aspect of generatrice, meaning every vector x can be written as a linear combination. Every vector x in E can be written as a linear combination of elements in this base B that I have here. Then I apply the f. Then I remember that f est une application linéaire, because that's what they are saying here. F une application linéaire, and so you'll be able to get this particular proposition that we have here. Now, one very interesting implication of what I've presented before you is now hold up. One very interesting implication is what? One very interesting implication is the fact that the linear application, one very interesting implication about what I've just shown you here is that a linear application is that a linear application is fully defined, is going to be fully defined by sort of like taking this composition with the basis elements. Like you might not understand what I mean by that. You basically sort of like understand, in maybe when we look at a few exercises, and maybe later on when I explain things, in great detail. Ok? Donc, on verra ça par la suite. Alors, so let's look at this definition that we have here. Nilpotence. The idea of nilpotence before we, So before the meeting cuts, let's look at the idea of nilpotence. Nilpotence. So we'll also look at this for les matrices. For les matrices, when we start le calcul matriciel, we also define, nilpotence. And by the way, let me first of all, explain what an endomorphism is. What an endomorphism is. So if you look at our linear application, is from an espace our linear application is from an espace E to another espace F. Now, if E is equal to F, then we're going to have an endomorphism, because this mapping is going to be within the same espace. If E is equal to F, then the mapping is simply from E to E. Okay? And then this is what an endomorphism is. So a mapping, for example, from R2 to R2 is an endomorphism. And then a mapping from R3 to R3 is an endomorphism. So this is an endomorphism. Now, if this endomorphism is bijective, so endomorphism plus bijective gives us a what? Gives us an automorphism. Endomorphism plus bijective gives us an automorphism. Now, bijective means what? Injective and what? Injective and surjective. So in linear algebra, we'll look at how you can show that a mapping, or that a linear mapping is what? Is injective, or a linear mapping is surjective. We'll look at how we can sort of like show how we'll be able to arrive at those conclusions in linear algebra. So if they tell you that montrer que l'application F est un automorphisme. If you want to show that it's an automorphism, you first of all check if the mapping is within the same espace. If it's within the same espace, it's an endomorphism. And then you check if the application is injective. You also check if the application is surjective. Then surjective plus injective is going to mean bijective. And so if the endomorphism plus bijective will give us an automorphism. So we'll look at examples where we'll be able to sort of like apply these things that I've described here. But hopefully for now it's clear what an endomorphism is. Automorphism is just an addition, a natural addition to what I'm describing here. Because if you talk about an endomorphism, the next step is, or the next thing that one is likely to do is to sort of like add the aspect of bijectivity, and now fully define what an automorphism is. So hopefully that is clear. So that's just a little digression on of what an endomorphism is. Donc soit E en cas espace vectoriel, un endomorphisme F de E est dit nilpotent s'il existe un entier naturel non nul K tel que F de K est égal à 0. What?
I have a question.
Okay.
Yeah, can you just repeat on the definitions? I'm mixing up some things like automorphism and isomorphism. Yeah, where is the different exactly? Like I'm kind of mixing up the information. So can you just explain
Between what?
automorphism and isomorphism?
Bien. So let's first, everything starts from an endomorphism, right? An endomorphism is a mapping within the same espace. An endomorphism is a mapping within the same what? Within the same espace. So from R2 to R2 is an endomorphism. From R3 to R3 is an endomorphism. Now, if endomorphism plus bijectivity gives us a what? An isomorphism is, we'll look at an isomorphism because for an isomorphism, well, first of all, look at the idea of dimensions. When you are given two spaces, let's say you're given some space E and you're given some space F. You're given some space E and then some space F. If the dimension of E is equal to the dimension of F, then we can simply say that these two spaces E and F are going to be isomorphic. So two espaces vectoriels are going to be isomorphic if they have the same dimension. So if E is an espace vectoriel and F is an espace vectoriel, and if the dimension of E is equal to the dimension of F, then the two spaces are going to be isomorphic. Meaning, if you are given the space E, and then if it's maybe, if you're given an espace E, if you're given the espace E, you can sort of like look at the espace F, and then every conclusion I make for the espace F is also going to be true for the espace E, because they are isomorphic. So deux espaces vectoriels are going to be isomorphic if their dimensions are equal. So l'espace E is going to be isomorphic to the espace F if the dimension of E is equal to the dimension of F. Endomorphism is a mapping within le même espace, R2, R2. Automorphism is an isomorphism that is bijective. Isomorphism that is bijective. Okay, is it clear?
Yeah, it's clear. I get the difference now.
Okay, so that is about, now we're talking about nilpotence. Sorry, I was about to sort of like go to the next page, but we've not talked about the main idea here. Donc soit E en K espace vectoriel, un endomorphisme F de E est dit nilpotent s'il existe un entier naturel non nul K tel que F à la puissance K is equal to 0. So here we must be very careful. S'il existe, let me first of all highlight, a few, maybe underline a few important, parts of this particular definition. S'il existe, if I find one item, okay, if I find that one item exists, then there's a chance that many other items are going to exist. And then I only have to find one, right? So if I find one, it doesn't mean that it doesn't necessarily mean that is the only item or the only element that satisfies the property. No. It means for that one particular item that I've found, there are many other items that can satisfy the same property. Now, in this case, we must be very clear about this K. Okay, what this K is. We must be very particular about this K. Well, this K has to be the minimum value. It has to be the minimum, the smallest, not the minimum, not the smallest, but the minimum. This K has to be the minimum value such that, now we know that K has to be an entier according to what the definition is saying. But here, c'est un entier non nul. So there's this word non nul, meaning K is going to be in N étoile, tel que F à la puissance K is equal to 0. Now, this is the precise definition of what K is. Okay, this is what K is. K has to be the minimum. For if I look at all the values of K, I say maybe, okay, 2 works, 3 works, 4 works, 5 works, F to the power maybe 6 works, F to the power 7 works. If all those work, then the K that I'm describing here, the K is the index, the K is what is known as the index of nilpotence. So l'indice de nilpotence. So c'est l'indice de nilpotence. K is known as l'indice de nilpotence. L'indice de nilpotence. So it is the minimum value of K such that this property here is true. The l'indice de nilpotence is the minimum value of K such that this property is what is true. Okay, the minimum value. And then this K is less than or equal to the dimension of E, where E is a finite finite vector space. Finite vector space. So we'll not show this property, we'll not demonstrate this property here, but this index of nilpotence is less than or equal to the dimension of E. So for example, the index of nilpotence of a linear mapping from R2 to R2 like so is actually going to be, K here is going to be less than or equal to 2. For R3 maybe to R3 like so, you see that the nilpotence here is going to be less than or equal to 3. Why? Because in the first case 2 is the dimension of R2 and then 3 is the dimension of R3 in this second situation. Okay, so this nilpotence is the minimum value such that f to the power k is going to be equal to what? Is going to be equal to 0. And then this nilpotence is less than or equal to the dimension of the space E, where E is a finite vector space. The definition for nilpotence, c'est clair? Ça marche? Je passe?
Can you repeat? I'm not sure. I've only heard the definition that it's the lowest
What?
minimum value. I've only
Minimum.
heard that it's the minimum.
Mhm.
I've only heard that it's the minimum value of k, but
It's
I don't
the
understand.
it's the minimum value of k such that this property f à la puissance k is equal to 0 is going to be true. So meaning it's the smallest, it's the minimum value. So for example, if you have 2, if 2 is a value for it works, if so here I've given you a few values here. So if f squared is equal to 0, f to the power 3 is equal to 0. F to the power, now what is this f to the power k? F to the power k is f rond f k times. Okay, this is like composing the function with itself k times. Okay, k times, this is what f to the power k is. So if you compose the function with itself 1 time, 2 times, and then you get 0, you get the 0 function. You do it for 3 times, you get the 0 function. Do it for 4 times, you get the 0 function. Do it 5 times, you get the 0 function. Then it works for 2 times, for 3 times, for 4 times, and then for 5 times. Then if the question comes, what is the nilpotence? The nilpotence in this particular case is going to be what? It's going to be the minimum of all those values of k. So it's the minimum of 2, 3, 4, and 5. So in that particular case, the nilpotence is going to be 2. Because 2 is the minimum value of k for which this property f à la puissance k is equal to 0 works. And then this second, what I've written here is another property which says, or which is saying in this particular case that the nilpotence is always less than or equal to the dimension of the space E, where E is a finite vector space. Now we're not going to demonstrate this particular property, but then it's something that you're supposed to remember, that the nilpotence is less than or equal to the dimension of E. So the takeaway here is that the nilpotence is the smallest value for which this property f à la puissance k is going to be equal to 0. F à la puissance k is composing the function with itself k times. So f à la puissance 2 is composing the function with itself 2 times. F à la puissance 3 is composing the function with itself 3 times. Now if I compose for 2 times I get the 0 function, and compose for 3 times and get the 0 function, then I have to take the minimum of those values of k. In that particular case, it's going to be what? It's going to be 2. C'est clair?
Yes, it's clear. It's like when I compose vector, the first time I don't find the 0. The second time I find the 0. And also the third time I find the 0. So I get the second time that I got the 0, right?
Yeah, so the nilpotence there is equal to 2. Even if it works for 3, 4, 4, and 5. So what we're going to do is that we're going to exit this meeting and then wait for the new link, and then we'll continue with our discussion.